and welcome to the recorded version of my masterclass HDA development for high precision environments. Now this is going to be structured a little differently to how it was done in the classroom, largely because you're here to rewatch the content we covered and not sit through a whole introductory PowerPoint presentation. But just to recap what we'll be covering today, we're going to look at some quality of life features that Q3D Studios likes to put into our HDAs when developing tools for our F1 simulation racetracks. Most of the HDAs we develop have very little manual input and serve to automate the translation from splines to track geometry, but covering that process is a bit much for a 90-minute masterclass. What I'm showing today will be some smaller features that can be put into manual placement nodes or automated nodes to improve the user experience and help stabilize what gets output. So, we're going to start with looking at some basic Python state scripting for placing points on the surface of another object. Then we're going to look at some ways you can build upon a simple multi-parm setup for better usability. And finally, we'll be looking at one method for caching and reading data using Python. Just to be clear, you're unlikely to use all of these features in the same HDA. There's many examples where you'd use 2 or 3, but it's rare for a tool to require everything at once. In fact, I'd recommend the first half of this talk for tools that require a lot of user interaction within the viewport, and I would recommend the caching for areas of the pipeline that rely on an interaction between automatically generated geometry and user parameters. For example, in F1, gaps in the crash barriers are painted orange for visibility. When we adjust the barrier splines every year, because the track has changed, the prim numbers are usually quite likely to change, or at least have their orders swapped around a little bit. We don't want to have to reassign all of the sizing data to the volumes that are generated at the end of the splines every year, so we can cache the data to a text file, and then we're able to reference this to preserve these parameters based on the locational data of these volumes, rather than having to tie it to anything relating to the splines that are input into the tool. For more information on our barrier pipeline, check out our project profile on the SideFX website, which goes into detail on the whole process. Now, without further delay, let's start producing our point placer tool. So for this, we're just going to need a nice blank HIP file. This shouldn't require anything external to it in order to follow along with the masterclass. So we're going to start off just by making a geometry node, and then inside of it, let's just make a subnetwork. The wonderful core to all HDAs, and we're just going to create a digital asset out of this, and you can call it whatever you like. I'm going to call it point placer, and you can just throw it anywhere. I'm just going to leave it a default for the moment. So now that we've got this HDA, our first step is going to be to create the core nodes and parameters for the functionality of the HDA. So we're going to start off by making a add SOP, I'm plugging that right in. And then we're going to come over here and create a null, and we're just going to call that collider. So the add SOP is going to be the node that is actually creating the points that we want, and the collider is going to be used to reference any collision geometry that we input into the HDA. And all we need to do then, go over to parameters, and we're going to just promote this number of points attribute up to the existing parameters section by holding Alt and middle mouse clicking, and it will broadcast that over to here. We don't actually need the weight attribute for this, so I'm just going to make it invisible to get it out of the way. What we'll have then is a parameter which determines whether or not a point is being used, and a vector parameter for the position of the point. So I'm going to come to the interactive panel, and we're just going to click New and create a add point state script. And then we're just going to accept that. Now, I'm by no means an expert on state scripting. If you need more information, there's probably going to be a lot of tutorials out there that will be able to give you far better knowledge than I have of it. Because what I'm about to show you is basically the extent of what I do. So, the first step, when you've got this, is that we're going to be adding a variable for logging all of the collision data that we're going to be getting. So, we're just going to type self.collision equals none. And this is just going to create a blank Python variable within the self state, which we're going to be able to access further on throughout it to add the collision data. So in the onEnter definition, what we're going to do is capture this collider null and take the geometry from it, holding it within that variable. So I'm just going to type self.collision equals self.node collider geometry with brackets at the end. So what we're doing here is we're taking self.node, which taken from above is literally just the current HDA reference, so the node that we are actually making at the moment, and this specific instance of that. And within that we are searching for a node called collider, which we have here. And then we are capturing the geometry data that is within inside of that. Okay. Then inside of onMouse event, what we're going to do is actually find the intersection with that geometry that we've captured and with a ray that gets cast from our click. So it's already got all of the stuff set up for actually doing the ray, and by default it's intersecting with the plane, the construction plane or the grid of the world, but we're just going to kind of step in and say no, we're not intersecting with the plane. We are going to say if we are hitting something that we are capturing from this collider, we're instead going to take the vector data of the point at which we have hit on that geometry. So for that, we're just going to go create a new variable called geoIntersect, and we're just going to go su.geometry intersector self.collision origin direction. Hold on. Now what this code is doing is that it's testing an intersection between the collision geometry and a ray that's been created earlier in the state script. If there's a valid intersection, it will return a geometry intersection object from which we can extract positional data. Then if the collision is successful, what we need to do is take the intersection position data and use it to overwrite this position here. So we're just going to go if geoIntersect.intersected. So essentially if the Boolean that has been captured by this first intersection has shown that there is an intersection between the ray and the geometry, then what we're going to do is just overwrite the position with the position of that intersection. And everything else should run as normal, just taking this data and using that instead of the construction plane data. And because you've got an if statement here, it means that if the collision is unsuccessful, then it will just revert back to this construction plane, which is perfect. We'll just apply that. Now, as far as collision geometry goes, you can use whatever you want. It could be a character model if you're making a tool to place something on that. In our case, we do whole environments, so for testing purposes you could just do a grid and with a mountain SOP connected to it to just create some rough terrain. What I'm going to do is just pull in some conform geometry that we have produced for Miami. So this is what a conform model looks like, that we produce with all of that lovely track surface data. And what we can do on the point placer node, so we should be able to click and it will add a point, and you can see there that the Y height of it is different. It's able to place these points in the viewport and actually capture the intersection data. If I miss it, it will create a value that is equivalent of 0 because it is just hitting the construction plane. But if we look here, you can see all the values are changing, including being able to scrub over the geometry, and it will capture that specific height point. Now, you can do this in other ways. You could have it placed on the construction plane, and then just have it raycast to a surface, but we quite like having it where it will actually have that height data from the get-go, so that we can adjust it and tweak it if, for example, we want to pull an object down so it's actually sunk into the ground a little bit. We'll be able to do that. Or if we need to float it, say we've got like a building that needs to be slightly more visible behind a barrier than perhaps the conformed geometry is allowing, we're able to do all of that in one place. Now, usually with a point placer function like this, we would do it internal to the HDA that we're developing. There's not much cause to create a standalone point placer node unless you feel like you're going to need that in a lot of areas of your pipeline. So instead, we prefer to just redo this function inside of the nodes that require it, because we just find that it keeps it a lot cleaner and tidier and leaves less room for user error if we're having to pass points between one node and another. So this is an example of one of the tools that we have which uses this function. This is an add gantry generator, and if you just click in the viewport, it will create a box which we can then scale, rotate, and just generally position whatever way we want. I've removed the advertising from it just for anonymity purposes, but yeah, you can just quickly pop that down, and the core of that is really just being able to click and place one of these gantries wherever you need it at the time. So now on to part 2. We're going to start by just making another subnetwork and converting that into digital asset, and we can just call this anything. I based this masterclass around a Marshall Tower generator that we have built, so might as well just call it that. Cool, and just leave everything else as default unless you want to change that. And we've now got another HDA. So step 1 is going to just be setting up a basic multi-palm. So we're just going to create a folder, bring it across, set it to multi-palm, and you can choose any of these really, but we're just going to go with scrolling because it finds it's quite nice. And we can just call this towers, like so. And then inside of there, we're going to essentially just put the kind of data that we would need to create a bounding box within the viewport. So we're just going to create a vector free to start with, and we're just going to call that size, and a single float, and we can just call that rotation, because we're only going to be rotating it around the y-axis, so only needs one. Now, because this is a multi-palm, these are going to need to have hashtags at the end of them to show which iteration of the multi-palm they are nested within. You can add that yourself manually, like so, or if you leave it blank and apply it, it will automatically add one for you. So now we have got a multi-palm with all of these inside of it. So what we're going to do as well, just for a bit of housekeeping, we're going to add a heading, and we can just say tower hashtag, and this hashtag will be replaced by the iteration number of the multi-palm. These you can call anything really. I'm just going to leave them as default for simplicity. But now we have got tower numbers over here. And now because we've got points coming in externally to this node, what we can do is just add a simple Python script that will allow us to populate this multi-palm and make it just a lot more user-friendly so that your artists aren't having to count how many points there are and put them in there or anything like that. So we can just create a Python SOP. I'm just going to close this menu for the moment. Okay. For those that don't know, it's just Alt-E to open up this other window. It can be a bit more user-friendly for when you're trying to enter in code. And what we're going to do, leave these bits at the top. I like to just add an additional variable for the HDA. So this is essentially the reference to the parent node, like the top level HDA for the specific node that you're working with. So you just put apostrophe, 2 dots, another apostrophe. This is very similar to when you're like trying to connect channels to things, and you'd go like channel ... All that this ... is meaning is the sort of parent directory of the current node that you're working with. So just one step up in the network view. And then what we're going to do is just identify the number of points that are being fed into this node. So we'll just create a new variable based on the length of an array of points. So that's len, and then in brackets geo.points. So get the points from the geometry, define the length of that. And then we're just going to go HDA.parm towers.set points. So this is taking the parent HDA node, identifying the towers parameter on it, which is what we called our multiparm, and it's setting the integer to the length value of the array of points. So basically just how many points are being fed in, and it will set the multiparm appropriately. Just apply that. So you can see here you've got 1 point coming in, and it's automatically created 1 tower. So we can just keep adding these like so, and this will populate appropriately. Now one thing that we're going to want to add is just some default values for these, otherwise whatever we create is going to be absolutely tiny. So we could just set these values to like 353, so 3 meter square base, 5 meters tall, and accept that. So now what we're going to do is actually do something with this data. We're going to read from the multiparm using a for loop. So we can just go for each number, plug that in. And what this does automatically is it creates a metadata node, which we can use to track the iterations, which is going to be important. I usually just call it something like meta, so that we're able to easily identify this within the other nodes for sort of quick extraction of the current iteration value. Then what we're going to do is we're going to just create a null, plug that in, call it read input, and this is going to just be used for the positional data of those points. And then we can create a bounding box node, so we'll just create a box, and I'll just call it bounding box. And for the sake of theatre, what I'm going to do is grab something I made earlier, just a little geometry generator, and this will take it and turn it into an actual Marshall tower. So I'll just up the size a bit on that to the defaults. There we go. How cute is that? And we can just plug that into the output. Nice. And then what we're going to do is set the iteration value to be equivalent to the length of the multiparm. So this is going to be our first actual channel reference, and we can just go channel ... and then towers. And this is now taking that integer value from the multiparm and using it to feed how many number of iterations are going through the for loop. And now for the bounding box itself, we're going to want to make sure that the center is the location of these points, and that the size is connected to the multiparm as well as the rotation. So what we're going to do first is we're going to just add a spare input and connect that to the meta node so that we're able to quickly get the iteration value from it. And you can do this each time, but I feel like it's appropriate to just create a iter value at the bottom of the node, which just makes for a bit faster reference when it comes to constantly having to refer back to what the current iteration is. I'll demonstrate. So you can go detail -1 iteration 0. So this is taking the detail attribute from the meta node called iteration. It is only a single channel float, but you still have to say that you're taking it from the first channel. and it will give you the iteration. Now this doesn't line up with the multi-palm, because multi-palms start from a value of 1 and the iteration starts from a value of 0. You can change that, but for usability I find that a lot of people seem to quite like it when the lists start from 1, especially if they're not programmers. So we can just go +1, and there we are. So now this can be referenced within all of these and used for connecting to those top level parameters. Now for this part, there's a couple of different ways that you can go about connecting these. You can either use a function called stringcat, which will concatenate 2 strings together, or you can just append strings together with just a plus sign. So I'll just demonstrate both quickly. So we can either do a channel rot underscore plus chs, so channel string, iter, and this will take that value from the top level. So if I set this to, say, 10, then this will be set to 10 in the final iteration. Or if you feel like it, you can instead go stringcat // rot underscore comma chs iter, and make sure you have enough brackets at the end, and this will also capture the same value. It's really just you're trying to create a string inside of this which will reference the specific multi-palm thread, which requires a little bit of dynamism. It requires you having to reference this iteration value as you go through it. So for this one it's a little bit more complicated because it has a vector that we're trying to reference. You have to have an XYZ value at the end of it. So we're just going to start it off the same way with a plus sign, the iteration value converted to a string with chs, and then just plus x, which will be referencing that. And we're just going to repeat the same for these others, y, z. So what we're going to do actually, in order to make this a bit easier to read, as I've just recalled that this is going to be a bit unnecessary, what we're going to do, instead of having it set like this, we're instead going to have it be by pieces or points instead, and have this extract piece or point. So now this should loop through. Yes. And instead of it being linked to the multi-palm, it will instead be linked to just the number of points, which is of course the same quantity. But what it will do is just isolate each individual point, which it wouldn't have done otherwise. So now we're just going to go point in read input, point number of 0, attribute of p, index of 0. So this will now just be reading the x value of the point that has been extracted by the for loop. And we can just copy and paste that into each of these. And the positional values will now be sorted. What would be good to do as well, because these points are placed on the ground, is that we're going to want to copy this parameter for the y size, and we're going to want to just add half of that. So plus channel size y divided by 2. And now you have a basic multi-palm setup where we're able to control each of these individually and adjust them. And what we can do as well, I'm going to just take this rotation value and cap the range at 360, just so that we can do a full spin with it now. Okay. And what we're going to add as well to it is just some simple guide geometry so that we're able to identify which of these is being used at any given time. So we're just going to add a font, add a spare input to that font, connect that to the meta, and on it we're just going to, instead of this, put backtick detail -1 iteration 0 + 1. And backticks, just whenever you're trying to type any Houdini code into a string, you're just going to want to add some backticks to it. And now it has created a font for whichever the current iteration number is. And we can go ahead and just merge that into here. We are going to want to group it to identify that it is a guide. And then for the position, we're going to want to copy the centroid location of this, paste relative references. And what we're going to do is we're going to just take the size value for the Y, and we're just going to add that on top so that it will just always sit above even when we adjust the height of it. Keep it nice and visible. You can always adjust the font size as well if you wish. Ooh, bit big. We'll go 2. And then when it comes out of here, we can just split that based on the guide geometry. And we're just going to create a null and call it guides. And then inside of the asset properties, we can come to node, and here there is a input for guide geometry. So this is just anything that will be visible as a template, even if it's not in the actual output of the node. And we can just type guides. Accept. And there you go. Now from outside of the node, you can still see that this is tower 2 and this is tower 1. And you can adjust them accordingly. And now we're going to just crack open Marshall Tower Generator type properties again. And what we're going to do is try and add handles to these. Now, because the centroid locations, the points, are being controlled by external geometry, I wouldn't recommend using handles in the way that I'm about to show you on it, just because without some additional editing within like the handle scripts and things like that, it will not update in time with it, but I'll still show you how to set them up anyway for if you wanted to have the point placer be internal to the node. So what we're going to start off by doing is just create a simple bounding box handle. And now this handles work by just having a variety of bindings that you can easily tie them to onto the various parameters inside of your HDA. It becomes a little bit more complicated with multi-palms because you're going to have handles that reference each individual one, unless you have handle scripts that are updating it live, but that's not an area that I have too much experience with. So I'm just going to show you how to do the simple setup using these, and there is a lot of different options for them. So for the most part, if you're trying to just make a quick HDA for something, you're probably going to be able to find some kind of handle within here that you may want to use for your tool. So we're going to start off with by just connecting to the things that we already have. So we'll just go size 1x, size 2, oops, 1y, size 1z, and set the ry to rot1. And then you would probably need to copy and paste these if you wanted to have it for the others, but I'll just show you how to set up one at the moment, and then I'll show you the insides of a slightly larger scale object. And what we're going to have to do is just create a parameter to keep track of these centroid locations. So what we're going to want to do is just create a float value, and we can call this, say, center x, sen x. And then we can set the size to be whatever we want. The maximum, I believe, is 16. Usually I tend to cap it at 16. I think the actual limit for handles tends to be about 30-something, 32 maybe. But 16 is usually probably going to be okay, especially if you're not planning to place down hundreds of points with a single node. So set it to a size of 16, and then you have all of these float channels which are can be used to reference point values. We can start off by literally just doing a point reference, so point 0, 0, p 0. And then you will have the actual value of the x of that point coming in be referenced there. What you're going to want to do as well, to make sure that you're not ending up with all of these being populated by the sort of maximum point number, you're going to want to multiply it by endpoints 0 greater than 0. So this is going to multiply it by just a 0 or 1 value of testing whether there's more points in the geometry than 0. Which, when you multiply this out to all of them, and obviously increasing the value as you go, so changing this to 1, this to 1, it will allow you to zero out the values of any of these which are not actually finding the value. And I'll demonstrate why this is important. Because, as you'll see here, even though there's only 2 towers, it's still finding a value in this third one, because it is just finding the highest point number and taking the value from that. But if you have this contingency placed inside of it, then it will zero out the values of any ones which are not actually existing. So now I've got it populated, so we've got all of these with these references inside of it. This is only necessary because the points are external to the node. If you've got the points inside of it, then you will have this point placer attributes here with these centroid locations, and these are going to be much more useful to you when doing this. So this is just if you're having points coming in from an external source. Usually you're going to be able to just do a reference to this attribute here, which will be inside of the multi-palm itself, and that's just a lot cleaner. So now what I've done is I've just populated this out to all of them and just swapped the channels from 0 to 1 to 2. So the X, Y, and Z channels, apply that. And you'll see that this has now got all of these values that it's capturing inside of here. One problem with this is that, as you can see here, the Y height is being set to the points themselves, so very low values, when in actuality you're going to want the handles to be halfway up the model. So what we're going to do for that is we're just going to add to this. We'll do it before the multiply. Add channel size 1 Y over 2, and we can just put brackets around that. And what this is going to do is this is going to take the size of the first instance of the multi-palm in the Y value and just half it, in the same way as we did it on the box inside of the for loop, to make it so that it sits on the floor rather than in the center of the floor. We're just adding that to it. And what I've done is just copied and pasted that to all of the others, and then you just change this value to an increasing integer, and it will just be 1 more than whatever the point number is. Apply that. And now those are sitting halfway up. So now what we're going to do is connect those values to this actual bounding box. So we can just go sen x1, sen y1, sen z1. Apply that. And if we recook the handle, we'll see it's sat inside of there. And as you can see, it falls off because it's not got the live updating thing that I mentioned earlier. So outside of the Y height, which will stay sticky because it's it being offset by another value, wouldn't do that from the bottom, see? But still quite useful, you can still pull it around and use it, but definitely much more usable in this state if you have it inside of the other node. Then what you can do is just create more bounding boxes and just fill it up with the same information, but for the other multi-palm instances. And we're just going to set all of these to be invisible and apply that so that they're hidden. So in the add gantry generator that we saw earlier, if you recall, we're able to pull and reposition it, and you'll see that it updates in real time. So the internals of this add gantry generator work in a very similar way to what I just described. It's got a load of invisible parameters which are being used to essentially keep track of any additional data that we need for the handles. So for example, taking the point positions and adding half of the height to it, as we did in the other one, for toggling the handles on or off. Also for like keeping just the value for the vector direction of this handle that's inside of it, just keeping that pointing down, and things like that. And then the actual handles themselves, interactive, it is just a load of them repeating, and there's definitely cleaner ways of doing this, I'm sure. If you were to get really into handle scripting, you should be able to just take the center location of these and adapt it to whatever one is currently in use. But for most things that you need to do, you're probably going to be able to just throw this down quickly, and it will work, because production time can be quite important sometimes. Okay, for our final part of this section on multi-palms, we are going to be looking at utilizing folders to isolate certain areas of the viewport, so that we can, if we say have lots of different things that we're editing at once, or things that are quite detailed, we're going to want to be able to control what is being seen at what time, so that we're better able to make the changes that we want to make on our specific geometries. First step is we're going to add another folder into this multi-palm, and we're just going to call it subfolder, and then we can call it tower hashtag, and we're going to actually just remove the heading because we're going to use this in place of that, and change it to a collapsible folder. We're just going to plug those in underneath, apply, and now our multi-palm has these collapsible folders in it that we're able to open to view the different parameters inside of it. What we're also going to want to do is add a integer value to this as a visibility tracker, essentially. So we're just going to call it viz tracker, and this is going to just be used to keep track of which folder is open at which time. And we're going to make this invisible eventually, but for the moment we'll just keep that visible. Then we're going to come up to scripts, and we're going to just create a custom Python module script and create a new definition inside of it. So def isolate active quargs. Quargs are essentially a dictionary of information that can be carried through inside of HDAs. So when you say click a button, you can send quargs into the definition that gets triggered by it, and from that you can do things like capture the node name, find out the value of the attribute that it's being sent from, finding which multi-palm it's nested inside of. But the one thing to remember is that the values brought from it are always strings. So if you're trying to read an integer value from it, you're going to need to convert it into an integer. So first things first, we're just going to get the current node, and we're going to find the value of the folder which is sending this, because we're going to tie this to the callback of these folders so that when you open it, it's going to trigger this script. So we're just going to say val equals integer quargs script value, and then we're going to just locate the tracking parameter that we made and use that to log which folder is open, or if the folder is being closed, we'll just set it back to 0. So tracker equals node.parm, and we're just finding that viz tracker parameter which we had created earlier. And then to find the index, so as in which multi-parm is being opened, we'll just go quargs script underscore multi-parm underscore index, close the square brackets and the integer brackets, and then if val equals 1, else 0. So this is just like a Python ternary operator. It's just a condensed way of doing sort of an if-else statement. So it's just going to say if the value is 1, so if the signal being sent from the folder is that the folder is being opened, then take the index of that specific multi-parm, or otherwise return 0. And then we're going to just set the tracker to that value. Apply that. And we're going to just come back to this subfolder, and we are going to connect it via the callback script. So we're going to just type who.pwd.hda module, lowercase hda, capital M in module, dot isolate active brackets quargs. So on this particular HDA node, find its HDA module, so the Python module that we were just writing, find the definition for isolate active inside of it, the function, and then send quargs to it basically and trigger it. Make sure this is set to Python as well. And now you'll see that it is sending it through so that when you're closing a folder, it sets it to 0. When you open it, it's setting the value to whichever folder is currently open. And then what we're going to do, just as a bit of tidiness, because as you can see here, you're able to open both at once, and that just sort of confuses things. We're going to go back to the scripts, and down here, we're just going to say if val equals 1, we're going to create a new variable called count, which is going to be the number of towers. So we're going to get the multi-parm attribute and evaluate it to get an integer value out of that. And then we can just loop through that. So for I in range count, v equals I plus 1. So creating a new attribute called v, just adding 1 to it. So basically, same as we've been doing this whole time, taking an iteration and just adding 1 to it so that it synchronizes up with the multi-parm. Then if v does not equals index, then node.parm subfolder plus string v dot set 0. So if the iteration value that we've got, the index, is not equal to the index of the folder that's currently open, then it's going to take this index, which we have shown to be not active, and just close that folder, so set it to 0. Folders are really working like toggles in this way, in that you can send it a 0 or a 1, and that just defines whether or not the folder is open. So we can set that, and now only one folder can be open at a time. Obviously, if you end up with hundreds of these, it's probably going to take a couple seconds when you open and close them, because you're doing a for loop. But for lower scale things, this works just fine. Okay, and now we need to actually do something with this information. So we can just set this viz tracker to be invisible because we don't need to see that anymore. And we're going to come inside of this node. So we're going to do two things with this information. We are going to adjust the alpha of the actual scaffolding itself, and we are going to adjust the color of the guide which is being used for it. So we're going to create an attribute wrangle, and we're going to create a new integer value at the top here for tracking it. So we're just going to go int active equals chai active, and you can call that anything you want really. We're just creating a separate little parameter up here. You can reference inside of here like you would with other things, but I just don't really like that. There's not really any reason to it. I think it's more superstition than anything. I just feel like having my things external to it just so that I can see it better, I guess. But it will now take the value of the viz tracker, so if we open that up, we should get a value of 2. Perfect. And then we can just set an alpha attribute. So for those that don't know, alpha, when put on vertices or points, maybe primitives as well, essentially is just a floating value between 0 and 1, which defines how translucent any of these surfaces are. So we can just go detail. Oh, we need to actually plug in the meta node first into the second input, because we need to get the iteration value. So 1 iteration plus 1 not equal active, and active does not equal 0. And this is another one of those ternary operators, just in VEX instead of Python. So this is basically an if statement. I'll explain how that works in a second, but we'll just set these values to 0.3 and 1. So if active is greater than 0, so if a folder is open, and the current iteration of the for loop is not equal to active, then it's going to set its translucency to about 30%. If either all folders are closed, or if the current iteration of the for loop is equal to whichever folder is open, then it will set the value to 1. So it's just a nice, neat way of switching the opacity of the Marshall towers based on whether or not they're open. So we can come look at this. We've got these two open, and as you can see, the translucency of them is affected by whether or not it is being viewed. And then we're going to do a similar thing over here. We can just go alpha control, duplicate this over here, go color control. And then this is going to do a fairly similar thing, but just instead of controlling the alpha, instead we're going to control the color attribute, so at CD. And what we can do is just set the colors for this. So we'll have 1, 0, 0 for red if the thing is currently disabled, and then we'll just have 1, 1, 1, so white if it is enabled, or just neutral. And now we can clearly see the opacity is dimming and the color is going off whenever we have that one not selected. So you can clearly see which one is currently being edited. And we could go one step further as well if we wanted to by creating a integer value and just call it like handle enable, and then we can just set that to be size of 16 and put something in it like channel viz tracker equals 1. And in order to have this work with a handle, it can't actually be invisible, otherwise it won't read it within the handle bindings. So instead we'll just have to do a little trickery by still having it hidden, by just putting in the hide when viz tracker greater than or equal to 0. And because it's always greater than or equal to 0, this will always be invisible even though it's not an actual invisible parameter. And you can just copy and paste this to all of the others and just obviously increase the value of that. And then if we come over to here, In the on-off, we can just connect this to handle enable 1, apply that, and now, there you go, doesn't update immediately always, but it will only be enabled when you have actually got Tower 1 active, and it'll be disabled otherwise. So you can genuinely only edit it in the viewport if you have that folder open. Now, onto the final and most fun part of the masterclass, looking at caching parameter data to text files. Since the masterclasses, it's come to my attention that this process can also be done by writing a dictionary of parameters and values to a JSON file. However, I'm still going to go through this process as I think it's worthwhile exercise to learn how to do this, and the ability to control exactly what data is cached and how can allow for some quite creative applications. But first, let's look at what problem we're actually trying to solve here. When you've got external data coming into one of your nodes, such as these points that we've placed, it's entirely possible that point numbers can change, especially if the data is generated automatically. So, for example, at Q3D, we will often extract data from point clouds and then have to extract it again the following year when we get new data from a racetrack. And almost always this results in a changing of primitive numbers, of point numbers, but very similar locational data, or at least approximately similar enough that we could use the locations of these splines or these points to bring forward values from previous years. So for example, we've got here our point placer and the HDA that we've made, and if we were to add a point in the middle of it, we would expect that it would probably mess this up. It would actually take the data from this second one and transfer it over to this third one that gets created, like so. Which obviously we can't have. If we are making a massive environment that requires really high precision, we need to be able to reliably say that if a point number changes, it's not going to affect any of the manual input that we've done into the node, and it will still produce a stable result that we can predict. So what would this look like? Well, for example here, we've got a little test scene that I made, and you'll see that if we were to add an additional point in between the first and second one, it will update all of the point numbers, shunting this into being the third tower, without actually changing any of the variables on it. All of the parameters will get carried forward onto this third tower, and even though previously it was tied to the point number, it's now instead been tied to the location of this tower, and therefore we've created a new one which has got default parameters placed here, and this one has maintained a stable relationship to it. The core functionality of this solution comes from these two Python nodes, one for reading data from a text file and one for writing data to a text file. As for the order of how this logic works, we begin by creating the write function, because when we do that, we're able to better structure what data is being written to the file, and then it makes it a lot easier to figure out exactly what you're needing to put into the read section of the function in order to decode that text, if you already know exactly the structure that is being used for the text file. Inside of the write node, what we're going to do is create a cache directory. Usually it will just be adjacent to wherever the HIP file is being saved. Then capture all point positions and their corresponding parameters, so finding the position of every single point and then seeing on the multipalm what attributes are being prescribed to this particular point. You're formatting these values into strings so that it can be writable to the text file, and then you're writing that array of positions and parameter data into the text file in that cache directory. Then for the read section, we're going to be opening and reading the cache file if it exists, i.e. the write function has already been run. Then we're converting these values back from strings by sort of reversing the encoding process that we're going to be creating in the write section. And then you're comparing the point positions of the current data to the cached positions inside of the text file. And wherever you find a inconsistency, so a position of a point does not align with the old attributes that were being prescribed to that point, then you can overwrite that parameter data on the top level of the HDA, and any new points, so ones where their positions aren't found anywhere in the text file, you're enforcing default values onto these sections of the multi-parm, just so that it doesn't keep that old parameter information and end up essentially creating a clone of one of the geometries. So let's begin. So to start with, we're going to create a Python node, and we're just going to call this write cache, and open up the window with Alt-E. So to start off with, similar to what we did earlier in the populate multi-parm node, we're going to just add a HDA line to this, so that we're referencing the HDA that this is nested inside of. And then we're going to create our directory. So this is going to be the name of the text file and the location in which it's going to be saved. So we're just going to go So what this string is essentially doing is it's using the expand string command to find out what the HIP reference is of the HIP file. So as you would usually type $HIP into somewhere and get the directory at which the HIP file is saved, by doing expand string it will do the exact same thing, but just in Python it will expand this out to be the current directory that the HIP file is saved to. Then we're adding /cache, so referencing a new folder essentially. Then adding the HIP file base name minus the extension, so minus the .hip part, the last 4 characters, then the underscore, then the HDA name, and then .text. You can really do whatever you want in this section. The goal is just to create a unique name that is unlikely to be the same as another file inside of the same HIP directory or inside of another one. So if you were to put something more generic here, it's quite likely that when it goes to write the cache, it might overwrite something that's been saved by another HIP file or another HDA. But by having the current name of the node and the base name of the HIP file itself, you're going to cover most situations. Just be careful if you were to say place down one of these HDAs in another GeoNode, that it has a different name to the one inside of this GeoNode. Then we're going to just create an array of all of the points on the current geometry. And then we're going to create a series of arrays which we'll use as containers for our positions, our scales, and our rotations. Then we're going to just do a for loop that loops through every point on the geometry. And we're going to start by creating a value for the current iteration in the same way as we've done in a lot of other areas. So just taking the current point number and adding 1 to it, and making sure that it's a string because we're going to be appending this to other strings later. We're then going to capture the position of the point in the current iteration of the loop. Then we're going to format it into a string that we can add to this pos list array. So when the position is run on a geometry point, it will return an array with 3 different floats indicating the sort of vector position, so X, Y, and Z. So because it's an array, we're going to use the map command to run through each instance of that array and just convert it into a string. In order to separate these areas of the array, even when they're concatenated into a single string, we're just going to add a comma between each of them. So iterating through each string in this array and just adding a comma to the end of it. And then we're going to just collapse it down into a single string. And then we're going to just take this string and append it to the end of our position list array. And that's going to be the positions formatted. Then for the scale, first we're going to create an empty array. And then we're going to just iterate through each of the X, Y, and Z axes. So we're creating a string array with X, Y, and Z as individual strings, and we're just going to iterate through each of them. Then we can append to our scale vector with each of the float values which we can find in the scale vector inside of the multi-parm. And here we're just accessing the size parameter on the HDA, and we're going to be appending to it the current iteration, therefore finding the particular instance of the multi-parm that it is nested within, and the axis, so X, Y, and Z. Similar to how we had to do this within the for loop, appending the iteration and the specific string for whether it's X, Y, and Z axis earlier. And then we're going to go through the exact same formatting process that we did with the position vector. And the same as with the position, once it's been formatted, we append it to the scale list. And finally, nice and simply, we're just going to capture the rotation and append it to its respective list. And all the formatting we need to do once we've captured the float from the particular parameter is convert it into a string. And now we're just going to press Shift Tab to exit this for loop, and we're going to combine all of these attribute lists. So to do this, we're just going to create a simple string array which just contains one thing. In this case, it's just going to be a hashtag. You can do any special character you like, but in this case, what we just need is something to indicate where the breaks between each of these arrays are. And then if you have a lot of parameters and positions that you're going to be condensing into a single array, then you probably could do this with a for loop, but because we've only got a couple to do, we're just going to create a new list, and it's just going to be a combination of all three of our previous lists separated by a hashtag. Lots of ways you can do that. Not necessarily the perfect way of doing it, but it certainly works. Now, unfortunately, when we're writing to a text file, line breaks aren't automatically added for us in between each of the indexes inside of the array. So we're going to have to add line breaks ourselves. So we're just going to iterate through the write list, and we're just going to add \n to it. And now each of the strings inside of this array is going to finish with a \n, and it will create a new line. So now we just need to write it to a file. And what I usually like to do is just add a if statement before continuing to the next part, because if you end up having no points plugged in and you don't have this statement to stop the next stage, then it will overwrite what is currently in the cache file with just a blank text file. So for example, say you've accidentally unplugged the input to the HDA and this node is still baked, then it will just delete your cache file, which is obviously not what we want. So by having this contingency in, it will just mean that in the event that the input has been unplugged, it's just going to do nothing. It's not going to finish running this script, it will just exit out without having to overwrite any of your existing cache data. So now we just run some simple Python commands which will open the directory for the cache file in write mode. So you can put all kinds of different strings here that will indicate whether it's read or write or read and write, etc. with the cache file. But in this case, we're just going to W for write. Now we've got a writable version of the cache file open inside of this variable. And then we can just run the write lines command, which will write each entry of this list, each on a new line thanks to this line break, inside of the text file, and then we simply close it. And that's the write file function complete. And we're just going to accept and close this. Now because annotating your code's always good, I'm just going to slowly tour through this annotated version of the code so that you can use it for reference in future. Now you'll notice immediately that it's going to be throwing an error because it can't find the cache file that it's trying to look for. Now if you recall on our order of operations list that we started with, creating a cache directory was the first step of this whole process. But even though logically that goes with the writing section, because physically the read node is going to be placed before the write node, because it makes sense to take the old data that you have before overwriting it with new data, we're going to actually put that function at the beginning of the read section so that if the cache file doesn't exist, it's going to skip over read and instead create a cache directory so that then the writing section can happen as intended. So now we're going to create the Python node for our read function. And throw that just in front of the write cache function. We're going to open up our editor. And to start with, we're going to need to import a new library of Python code. We're just going to go import OS. So we're bringing in operating system commands. And then under here, we're first going to add the HDA reference. And add an initial directory variable. So you'll notice this is the same as the directory inside of the right node, just without all of the additional names such as the current HIP name or the node name. And that's because to start with, we're just going to be looking to see if the folder itself exists. So if os.path.exists directory, so we're just running an if statement to check to see if that folder exists currently, is false. So if it doesn't exist, os.mkdir. So this is just making that directory. So if the folder doesn't exist, make the folder. And this is going to be important because otherwise without this you're not going to be able to create a cache file in that cache folder because there's not going to be a folder there in the first place. However, if that directory does already exist, so we're just going to go else, we're going to append the rest of our file name to our directory. So directory plus equals the base name of our HIP file minus the last 4 characters plus an underscore plus the name of our parent node and the text file extension. Then we're going to open that directory to get our cache file. And this time R for read, because we don't need to write any data to it. Then from that cache file, we're going to extract our cache. Instead of write lines, we're going to be reading lines. And what read lines does is it's going to take every new line inside of that text file and add as a new index inside of an array. So we're going to end up with a string array where every new line in the text file is a new value inside of the array. And then we're going to just close our cache file. Then, first part of processing this data is we're going to remove all of those line breaks from our strings. So you know the \ns, we're going to get rid of those. And we're going to iterate through every string in this array, just removing the end of the string. And then we're going to be producing an array of arrays of sorts. So we're going to take it from one massive array of strings into 3 smaller arrays, which are going to be our position values, scale values, and rotational values by splitting it at the hashtags that we added. So we're just going to do a for loop, and because we know there's only 2 hashtags in it, we're going to do a for loop with 2 iterations. If you didn't know how many hashtags you had, or you wanted to make it more dynamic, you could instead just have it count how many there are in the array, and then iterate using that. We're going to start off by finding the index of the first hashtag inside of the cache array. And then to the cache list, we're going to append every string from before that array. Then we're going to truncate our cache array so that it is just the things after that index. And then once that's done, there'll still be one section of the array left inside of the cache, and we're going to just extract that. We're going out of the for loop and just appending the cache one last time. So it might be a little confusing as to what result we've gotten out of this now. So what we're going to do is just print these 2 values and see what the difference is. So this is the difference between the 2 outputs. On the left we have the original cache that got extracted from the text file, and on the right is the cache list that we've produced by splitting it out. On the left you'll see that it is a single array where it's got all of our positional values, then a hashtag, then the scales, then another hashtag, and then the rotations. Meanwhile on the right here, we've actually got 3 separate arrays, all nested within one another, with no separating hashtags, and it's instead separated out all the positions, all the scales, and all the rotations into these isolated individual arrays, which we can then extract individually and run our decoding logic onto. So, first step, just for optimization, we're going to check to see if our point values have changed at all between this cook of the HDA and the previous cook where the cache file had been saved. So we're just going to see if there's a different amount of points. And if there is a different quantity of points, we're going to create an array to see which points have been updated. And then another array of axis information, just so that we can reference it easier later. And this is very similar to what we did earlier, where we just created a string array with X, Y, and Z axes in it, so we can iterate through them more easily. Then we're going to do a for loop that's going to just iterate over all of the cached points that are currently inside of the cache file. And to start with, we're going to convert all of those string vectors that we had contained inside of the positional area of our cache file, and we're just going to convert them back into float vectors. So we're isolating the first section of our cache list array, which is the positions, and then whichever the current iteration of our for loop is, we're going to be extracting that positional value, and then using the commas inside of that string to split it into an array of 3 different strings. And then we're going to just convert those 3 strings into float values. Then we're going to check to see if any of the current points in our geometry are within 1 meter of these cached positional values. And then because we have found a point within that range, we're going to take our old cache data and overwrite what is currently on the multi-palm with that cached data. Now this won't be updating it in the event that you've just changed the parameters, because we're checking to see if point quantities are different. So this is only going to happen if we've added or removed a point. And to start with, we just need to add to our updated points list this current point, just so that we can keep track that we have overwritten the parameter values of that specific point, to prevent us from reverting it back to defaults in a minute, but I'll explain that in a second. And if we have successfully found a point, we're going to create an iteration value, and then convert our size vector from a string back into a series of floats. And then we're going to assign this to the size parameter on the HDA. So the same as when we were taking these float values earlier to write them to the text file, we are finding the parameter again by taking the iteration and the X, Y, Z axes, and then we're just setting it to the particular index of our size array that we've just created out of that string. And then we just need to set the rotation as well. So now all of the points that have cached positions equal to their current positions will have their parameters overwritten by what is currently cached. So if you were to add a new point and suddenly point 2 has become point 3, as long as the position of point 3 has remained the same, all of its old parameter data will be overwritten on itself in order to carry that forward with it when its point number has changed. But in this event where a point number has changed, where 2 has become 3, the point that's been added into point 2's index has still got all of its parameter data. We've overwritten what is going to be on point 3 with the parameter data, but point 2 is still holding on to it and is therefore creating a clone of it. So we need to reset all of its parameter data to defaults. We're going to start by iterating through each of the points on the geometry and check to see if any of these points is in the updated points array that we've been creating this whole time. So this is where it comes into play. Any point that has not had its parameter data overwritten is therefore a point that was not found to be in the same position as a previously cached point. Therefore, it needs its parameters reverted back to default settings. Create an iteration value, and we just run the Houdini command to revert to defaults, iterating over each of the axes in X, Y, Z that we had created before to revert all of the entries in the size vector back to its default settings, and then we're going to just do the same for rotation. And there we are. We should now have 2 nodes which will successfully read and write to a cache file. And if this is working as intended, you'll have a text file that looks a little something like this, where it's got the positions of the point captured, the size of the Marshall tower that's connected to that point, and then the rotation of it. and these are all set automatically by that Python node. So now, instead of attributes being all messed up whenever a new point is inserted, now it will remain consistent. And as before, here's a slow tour of the annotated version, just for your notes. So where are some places that this can be used? Now, obviously, in this case, we're using it to help stabilize parameters, so that if point numbers change, it is going to keep the parameter data static and not cause geometry to go absolutely haywire, which is a perfectly valid way of doing it. Although, as mentioned earlier, you can do this specific thing by using a JSON dictionary, which will save a lot of time with the encoding and decoding, and is definitely something that I'll be looking more into in future. But some other fun things you can do with this: you can either create an external text file with pre-existing attributes. So for example, in our barrier generator, we have a list of UV values saved which show where logos are on the barriers, so that we can easily test to see if anything that we've done in the generation process has cut a logo in half, and then we can do something about that. So that you can save data that's been produced outside of Houdini in its own text file, and then reference that in various locations throughout your projects. Or, if you're getting really fancy, with our tracer bot, Tracy, as some of you may recall from last year's presentation, in order to not have to rebake every single iteration of itself every time a value changes, because Tracy can be quite slow, we will cache data as to what the current parameters are on the tracer bot, and only rebake bots that have had parameters updated since the last time it was cooked. So if the rotation or the field of view hasn't changed on a bot, it will just skip straight over it and read from a cached version of the geometry, rather than re-cooking all of that geometry from scratch. So thank you very much for listening. I sincerely hope you've enjoyed this masterclass. As mentioned, there's lots of things that can be improved. Houdini is an endless source of inspiration, and it has always new things that you can learn from it and learn about it. And I'm definitely still learning a lot of things, but hopefully some of the things in this course have given you some inspiration for maybe a couple things to try when you're making your next HDA, just to help improve the quality of life of your artists, because as technical artists, that's what we're here to do. Thank you very much.